Let's jump right into this explainer. Today, we're basically putting on our detective hats. Imagine trying to solve a scientific investigation into the literally invisible. We're going to look at a process that takes the completely unseen components of our world and makes them measurable, quantifiable, and, well, visible. It's an awesome journey from mystery to mastery. So let's get right into it. So think about this relatable problem. Imagine you've got a dissolved drug tablet sitting in a clear, completely colorless liquid. You know the active drug is in there somewhere, right? But there are also probably impurities, degradation products, or extra fillers hiding inside. You can't just look at it and know what's there. I mean, it just looks like a glass of water. So how in the world do you find out exactly what is hiding inside that mixture? Section 1. The Clear Liquid Mystery, Decoding HPLC. To actually solve this mystery, we need a highly specific technique to physically pull apart these hidden compounds so we can measure them. And the hero of our story is high-performance liquid chromatography, or, thankfully, HPLC for short. Basically, it's an analytical chemistry technique used to physically separate, identify, and quantify each individual component in a liquid mixture. The absolutely crucial takeaway here is that HPLC doesn't just separate the stuff. It tells us exactly what those hidden compounds are and precisely how much of them we're holding. Now, this specific ability gives HPLC a massive, massive footprint in the pharmaceutical industry. Honestly, it's everywhere. We use it for checking drug purity, catching those unwanted impurities before they ever reach a patient. We use it for assay testing to confirm the exact amounts of the active ingredients. We've even do stability testing to see how a drug degrades over time sitting on a pharmacy shelf. It handles dissolution and content uniformity too, just ensuring every single pill in a giant batch does exactly what it's designed to do. Section 2, Separation by Speed, the core idea. Right at the mechanical heart of this whole process is this constant, ongoing battle between two fundamental forces. On one side, we have this stationary phase. This is a solid material packed really tightly inside a column that stays entirely still. Fighting against it is the mobile phase, which is a liquid solvent that flows continuously. Now, when a sample mixture gets injected into this system, every single compound in that sample interacts a bit differently with these two competing phases. I love this analogy because it brilliantly illustrates the concept. Think of it like a group of runners with different speeds spreading out along a racetrack. As the mixture travels through the column, the compounds that interact really strongly with that solid stationary phase, well, they get slowed down. They take their sweet time. But on the flip side, compounds that interact weakly with it just breeze right on through, moving super quickly with the flowing liquid. Because every compound moves at its own unique speed, they physically separate from each other, eventually popping out of the column one by one. Section 3. Inside the HPLC system, the journey of a sample. Okay, let's follow just a single drop of our mystery mixture on a physical journey right through the machine. There are 5 distinct stations that map out its exact path. We've got the solvent reservoir, the pump, the injector, the column, and finally, the detector. We're kind of building a spatial map of the hardware in your mind right now, so let's look a bit closer at each one of these. First up, the pump. Its whole job is pulling liquid from the solvent reservoir and pushing that mobile phase through the entire system at a super precise constant flow rate. And it does this at incredibly high pressure, reaching several thousand psi. To put that into perspective for you, that is like the crushing pressure thousands of feet deep at the bottom of the ocean. So yeah, this isn't your grandma's chemistry set. This extreme pressure is literally exactly where the high-performance part of the HPLC name comes from. Next up is the injector. Now this is where the magic really begins for our specific sample. The injector introduces a very precise, super small volume of the sample directly into that flowing, high-pressure mobile phase stream. This is literally the starting line for our runners, where that clear liquid mystery mixture first enters the track. From the injector, our sample hits the column. Make no mistake, this is the absolute heart of the system. It's essentially a narrow metal tube packed with those tiny stationary phase particles we talked about earlier. And actually, the choice of column is the single biggest factor in dictating how well your compounds will separate. It acts as the varied terrain of our racetrack, testing each runner's specific speed and interaction. Finally, our runners cross the finish line and enter the detector. Sitting right at the very end of the column, this device detects each exiting compound the second it leaves. Very commonly, it uses UV vis to measure exactly how much light a compound absorbs. You can think of the detector as the finish line camera, instantly converting those physical, chemical exits into a perfectly readable electrical signal. Section 4. Reading the chromatogram, the translation. So that translation process gives us what's called a chromatogram. It's the output graph of an HPLC run, and it shows each separated compound as a distinct peak. You'll see time plotted on the x-axis and the detector signal, or absorbance, on the y-axis. This graph right here is the ultimate answer to our clear liquid mystery. It literally turns invisible chemicals into a highly visual story that we can analyze. Let's break that visual story down into two really key metrics. First, there's retention time. That's simply how long it took the compound to travel the entire length of the column. This metric tells us what the compound is by comparing its specific time to known standards. Then we look at the peak area, literally the physical space under that specific peak on the graph. This identifies how much of the compound is present. So remember, time gives you the identity, and area gives you the exact quantity. Now, a well-developed method is going to give you beautifully sharp symmetrical peaks. But what if things go wrong? Well, you might see tailing peaks, overlapping peaks, or maybe just excessive baseline noise. If your chromatogram looks messy, listen, these aren't just frustrating errors. These specific shapes are actually huge clues for troubleshooting exactly what is going wrong within the system's chemistry or the hardware itself. Section 5. Why it actually matters. The stakes. Let's do a quick comparison of the past versus the present. Old school liquid chromatography relied purely on gravity, took literally hours to slowly drip through a column, and honestly yielded incredibly poor separation. Contrast that with modern HPLC. We've got high-pressure pumps forcing liquid through stationary particles that are just a few micrometers wide. It takes minutes, and it provides razor-sharp resolution. This brilliantly illustrates the evolutionary leap in the lab. Having those tiny micrometer particles means vastly more surface area for interaction, which basically turns what used to be a full day's work into a quick coffee break. But hey, with high performance comes high responsibility. Why are these fundamentals absolutely critical to know before you even lay a finger on the machine? Well, because HPLC instruments and the highly specialized solvents they use are incredibly expensive. A simple mistake can permanently ruin a fragile column. Plus, if you're developing methods, you really have to understand how all these different parameters interact with one another. And honestly, day-to-day troubleshooting relies entirely on these theoretical concepts. You absolutely need to build a rock-solid mental model, because in a real quality control lab, a simple misunderstanding of these basics can easily cost thousands of dollars in ruined equipment or delayed results. So, to test your new mental model, think about this. If you change just one single variable, let's say adjusting the temperature or tweaking the flow rate of the pump, how exactly would that alter the runners on your racetrack and completely reshape your final chromatogram? I'm going to leave you with that provocative thought to challenge your intuition, and I highly recommend testing your theories on an HPLC simulator to safely see the results for yourself. Thanks for joining me on this explainer, and keep questioning the invisible.